Good day, everyone. My name is Sofia Nurada, and today we will present our project titled Stroke Prediction Using Machine Learning Techniques for Machine Learning course. This project aims to explore how machine learning can help predict stroke risk effectively. Okay, here's a brief outline of what we will cover today, starting from a literature review and problem statement, followed by our objectives, methodology, and an introduction to the study. We will then discuss the results, the limitations incorporated, future directions, and conclude the findings. Okay, so stroke is a leading cause of death and disability worldwide. Early, early prediction is vital to enable timely medical intervention and reduce health risks. This study applies machine learning techniques to predict stroke risk using a public dataset from Kaggle, which includes features such as age, hypertension, heart disease, and glucose levels. After, after pre-processing the data, we implement several supervised learning models such as logistic regression, random forest, naive Bayes, and decision trees, and evaluated their performance. And our goal is to identify the most accurate model to support early stroke detection in healthcare settings. And now for the literature review, recent studies have applied a range of machine learning techniques to improve stroke and heart disease predictions. Random forest and ensemble model consistently showed strong performance across multiple studies. Common datasets include patient health records from Kaggle, focusing on features such as age, gender, hypertension, heart disease, and glucose level. Our tools like Python, scikit-learn, TensorFlow, and XGBoost were widely used for implementation. However, limitations like data imbalance and small dataset sizes were common. Future work suggests using larger, more diverse datasets and integrating deep learning methods to enhance performance. And then for our problem statement, stroke is a critical medical condition that can lead to permanent disability or death if not detected early. Traditional diagnostic methods may not be sufficient for early and accurate prediction due to complexity of patient health data. With the rise of machine learning, there's an opportunity to improve stroke risk prediction using data-driven approaches. However, challenges such as imbalanced dataset, inconsistent data quality, and varying model performance need to be addressed. And which machine learning algorithm provides the most accurate and reliable prediction of stroke risk based on clinical and demographic data? To evaluate and compare the performance of various machine learning algorithms, including logistic regression, F-bias, decision tree, and random forest in predicting stroke risk. And to apply comprehensive data preprocessing technique to improve model accuracy and reliable prediction of stroke risk. And then to identify key risk factors contributing to stroke prediction, and then the last to determine the most effective model for potential use in health decision support system. Okay, my next is my friend.
Good morning, I'm Sai Kumar. I'm going to explain methodology. We followed a structured approach to develop our stroke prediction models. First, we acquire a dataset from Kaggle containing patient information with features like age, gender, hypertension status, glucose levels, and stroke occurrence. After the data acquisition, we performed through pre-processing including handling machine values. encoding categorical values and addressing the class imbalance problem since stroke cases were significantly underrepresented. We then split our dataset into training and testing sets with an 80-20 ratio to properly evaluate model performance. For the modeling phase, we implemented 5 algorithms: logistic regression, random forest, XGBoost, and decision tree, and Navy Base. Finally, we evaluated each model using multiple metrics including accuracy, precision, recall, F1 force, and drop AUC to get comparison understanding of performance, especially given our imbalanced dataset. Now going to result. Looking at our exploratory data analysis results, we can clearly see the significant classes imbalance problems. The first chart shows the distribution of stroke cases, where the majority of records are non-stroke cases, with only a small portion representing actual stroke incidents. Similarly, we examine the hypertension. Most patients do not have hypertension, though there is a noticeable minority who do. The gender distribution shows more female participants than male in our dataset. The bottom right chart confirms the hypertension distribution we saw earlier, showing that most patients do not have this condition. This imbalance in our data was one of our biggest challenge when building accurate prediction models. Now going to another results. Continuing with our data exploration, we analyzed several other important features. The residence type distribution shows a fairly even split between urban and rural residents, with slightly more urban dwellers. For work type, private employment dominates the dataset with self-employed, a government job, and children categories having similar but much lower frequencies. The age distribution reveals a wide range of participants with notable peaks around age 40, 60, 80, suggesting a multimodal distribution that could reflect varying risk factors at different lifestyles. Finally, the glucose level distribution shows most values clustered between 50 and 125, with a long tail extending to higher values. There is also a small secondary peak around 200, which is interesting since evaluated glucose levels are known risk factors for stroke. Now, our logistic regression model achieved an accuracy of 96.33 percentage, which initially seems impressive. However, the confusion matrix reveals a critical issue. It predicted zero positive stroke cases. This means all 32 actual stroke cases were misclassified. This explains the precision, recall, and FN scores of 0. Despite this, the ROC-AUC score was 0.6704 for India, indicating the most have model has some discriminability even though it didn't currently identifying any stroke cases at the default threshold. These results highlight when accuracy alone is misleading for imbalanced datasets. The model simply predicted the majority classes for all instances, which achieves high accuracy but completely fails at the actual task of identifying stroke risks. Now, the random forest model shows similar performance to logistic regression with an identical accuracy of 96.33%. However, it also suffered from the same fundamental issues facing failing to predict any positive stroke cases as shown in the confusion matrix. Like the logistic regression model, precision recall and F1 scores were all zero due to this. The ROC-AUC score was slightly lower at 0.6357, but still indicates some ability to rank cases by risk. Even if The default threshold didn't result in any positive predictions. These results from both models underscore the challenges of working with highly imbalanced datasets in healthcare applications. Despite high accuracy, neither model was effective at identifying the critical minority classes, patients at risk of strokes. Thank you.
Hello, my name is Dwi Rahma Utami. So here we have the XGBoost results. For the XGBoost model shows a slightly lower accuracy of 95.30%. Here we start to see some improvement in correctly identifying stroke cases, although it's still limited. Precision is 0.5, recall is 0.9, and the F1 score is 0.9. The ROC is 0.6863. Looking at the confusion matrix, we have 829 true negatives, 2 true positives, 30 false negatives, and 11 false positives. This indicates that XGBoost is beginning to pick up some positive cases but still has a high number of false negatives. Next, for the decision tree model, the accuracy drops further to 93.12%. The precision, recall, and F1 score are all 0.9. The ROC is 0.5284. The confusion metric shows 809 true negatives, 3 true positives, 29 false negatives, and 31 false positives. The decision tree's performance suggests it's also facing challenges in accurately predicting stroke, with a notable increase in false positives compared to XGBoost. Next, the naive Bayes model shows a significantly lower accuracy of 40.94%. However, it exhibits a high recall of 0.84, meaning it correctly identifies a large proportion of the actual stroke cases. Conversely, the precision is very low at 0.5, indicating many false positives. The F1 score is 0.9 and the ROC is 0.6971. The confusion matrix reveals a large number of false positives and a smaller number of false negatives, with 330 true negatives and 27 true positives. This model prioritizes catching as many stroke cases as possible, even at the cost of many incorrect positive predictions. Now let's compare the overall accuracy of all the models. As we can see, logistic regression and random forest achieve the highest accuracy, both close to 96.3%. XGBoost and decision tree followed by slightly lower accuracy scores, and naive Bayes has the lowest accuracy. However, it's important to remember that accuracy alone doesn't tell the whole story. We need to consider the other metrics, especially precision and recall, to understand each model's strengths and weaknesses. Overall, logistic regression and random forest appear to be the best model in terms of accuracy, but the other metrics reveal significant limitation in their ability to predict stroke cases effectively. Next, for limitations, it's important to acknowledge the limitations of our study. Firstly, we face a significant data imbalance with far more non-stroke cases than stroke cases. This imbalance can bias the models, leading to high accuracy in predicting the majority class but poor performance in identifying the minority class, which in our case is stroke. Secondly, the dataset was sourced from Kaggle. While it's a valuable research, public datasets may already be pre-processed and might not fully capture the complexities and noise of real-world clinical data. Model interpretability is another concern. Complex models like random forests and neural networks can achieve high accuracy but are often black boxes, making it difficult to understand how they arrive at predictions. This lack of transparency can be a challenge in medical settings where understanding the reasoning behind a prediction is crucial. Lastly, our dataset had limited feature diversity. It included only basic clinical and demographic information and lacked and lack potentially important factors like genetic data, medical imaging, or detailed patient history, which could provide a more comprehensive view of stroke risk. Next, for future study, to build upon this study and improve stroke prediction, several avenues for future researching are promising. Expanding the dataset with larger and more diverse data, ideally from real hospital records, is essential to enhance the generalizability and robustness of the models. Addressing the class imbalance is critical. Techniques like smooth or cost-sensitive learning can help to balance the data and improve the prediction of stroke cases. Integrating deep learning methods such as CNS or LSTMs could be explored to capture more complex patterns, especially in temporal or imaging data. Incorporating explainable AI frameworks like SHAP or LIME is crucial to make the models more transparent and provide explanations for their predictions, which is vital for clinical trust and adoptions. Finally, combining different types of data, such as structured data with medical imaging or electronic health records, through multimodal data fusion could lead to more holistic and accurate prediction models. In conclusion, our study demonstrates the promising potential of machine learning to predict stroke risk with high accuracy. Among the models we test, logistic regression and random forest showed the best performance, achieving accuracy rates close to 96%. These results indicate that machine learning can be a valuable tool to support early stroke detection and improve clinical decision making. However, we also encounter significant challenges, particularly data imbalance and limited feature diversity. Addressing these issues through larger, more balanced datasets and enhancing model explainability will be crucial for the continued advancement of machine learning in stroke prediction. Ultimately, machine learning models provide a strong foundation for developing more effective and proactive stroke prevention strategies in healthcare. Okay, so this concludes our presentations. Thank you